In the name of God, the merciful, the compassionate. Hello everyone, welcome to this lecture of software testing. In this lecture, we talk about the model-driven test design, which is the title of the chapter 2 in my textbook. Okay. In the first slide, we talk about the complexity of software products, or the complexity of testing software products. The first statement, the first item in this slide in all engineering fields, and there is a question why the software products are the most complicated products. There are several reasons for this complexity. I'll mention some of them in this lecture. But you know probably some others. The first reason for this complexity, as I believe, is the complication of problem space. In software systems, actually we have a complex problems to be solved, which consists of several different and conflicting requirements. The requirements sometimes in opposite of the other requirements. We have some requirements which conflict with other requirements. For example, in some systems we should promote the performance of the system. For promotion the performance, we should raise the availability, raise the throughput, decrease response time. But on the other hand, some requirements such as security needs more time and more computations to be done. So these two requirements often conflict with each other. And there are hard problems in communication with users in software products, in software projects. We don't notice very well our users, our needs of our stakeholders. They have an ambiguous mentions and ambiguous thoughts of the problem. So we should try to find out them, to got them got their needs, their actual needs. So the second reason is the hardness of communication with software users. And the next reason is that the requirements in software project are changed very often. Very often the users say, please change this area of this requirement, this functionality. It's a severe problem for developing good software. So changing is happen very often in software lifecycle, software development lifecycle. This is another reason for the complication, for the complexity of software products. The other reason is complication of software development process. Usually software development process as not routine as in other fields of engineering. Okay. And the next reason, as I believe, is the flexibility of software products. And at the same time, the lack of standards as in other engineering fields, such as building, such as car industry, such as other fields in industry. And as you see in this slide, as you see, the correctness is a severe problem in for software products, but it's not for other fields of engineering. As the slide said, the term correctness has no meaning for these questions. Is the building correct? It's meaningless in building industry. Is a car correct? Is a car correct? Has no meaning in mechanical industry, in car industry. Is the subway system correct? The correctness of subway system does not verify by its specialists, and this is meaningless in this industry. But in software products, the correctness is the main problem, is essential. The correctness of each software product should be verified by software engineers, and the correctness and the proving of correctness of the software is very hard, it's complicated. So the software product is the most complication product in engineering fields. For handle this complexity in software industry, usually we use an abstraction. The abstraction is a keyword to manage the complexity of software projects. It is also used in other engineering. Okay. So in this book and in this class, we focus on the model-driven test design approach. This approach uses model to raise abstraction level of the problem. When we raise the abstraction, some details are ignored, and some essential points are highlighted. So in model-driven test design, we use models to raise abstraction to prevent encounter with some unnecessary details, but details that should be focused on are highlighted on the models. So the model is an abstract structure, and we use a model-driven approach to design test data, to design our test cases. As we will see in the next or this section, this lecture, we use some models that extracted from source code, or some models that is designed in a design stage of the software life cycle, or we can use some formal methods to specify the behavior of software that the target system. So we can use this model as an abstract structure to design our test cases, and we can prevent to directly work on, for example, source code or other specifications of the project. So we will focus on model-driven test design approach to handle the complexity of testing software, or handle the complexity of software testing in this lecture. But an essential point that you should note in this slide, is testing can only show the presence of failure, but not their absence. Why? Actually, in software testing, we say that the testing cannot prove the correctness of the software. In the software testing, we try to reveal some software failures. We try to reveal some software faults. But if we can't do it, if we can't to show the failures by testing, this not means that the software is overall correct. So the software testing just promote the level of confidentiality of using the software product. Okay, software testing is just for raise the confidentiality of using the software product to some level, to acceptable level, but not for proving the correctness of software. The correctness of some software products, such as safety critical systems, should be done by other ways, such as theorem proving, such as formal verification, which is done by model checking tools or model checkers. So the correctness, so the proving of correctness of the software product is very hard and it is not the scope of this course. The scope of this course is software testing, which just try to reveal more failure, to reveal more faults in the system, in the software products. So we summarize that testing can only show the presence of failures, not their absence. In this slide, 3 terms are defined. The first one is testing. What's the meaning of testing? It's simple. It is the evaluating of software product by observing its execution. How we observe its execution? How we can observe the software product execution? For example, in the simplest form, when we call a method, we feed it the method by some input values. And we receive, after execution, an output of the method call. For the feeded input, I should guess the expected result. I should compute the expected result manually, and after execution, we can see the output of the method call, and we can compare the output, the actual result, with the expected. If this is two the same, the execution is successful and the testing is done, is passed. The test is passed. But when the expected result, as I said in the previous lectures, when the actual result is different from the expected one, we say that the test failed, and we have a test failure. So the test failure is the execution of a test that results in a software failure. We have defined the software failure. The software failure occurs just when the expected result is different from the actual result. And when this is observed, we should try to detect whether the software is faulty or our test has a problem. If the software has fault, that should be fixed. In other than, the test should be changed and corrected. It may be that the test be incorrect or be faulty. When the software fault is detected, we should fix them. We say that this is debugging. The debugging is the process of finding a fault given a failure. The process of finding, the process of look for a software fault, a faulty statement in the software, or faulty statements in the software that leads to a late failure. Okay. So in your study project, I asked some of you to research on fault localization. in which we are trying to find out the location of faults in the software, which lead to a failure. So software fault localization is an active research area today. Behind this, the software fault prediction is the same. It's also an active research area in software testing, software fault localization, software fault prediction, and so on. In this box at the end of the slide, it's highlighted that not all inputs will trigger a fault into causing a failure. As you have seen in the previous lecture, some faults, some inputs making a correct execution, making a true execution, and there is no any fault in any failure by some input values. This is overall true for all software products. This is because the reason of this is that for observing, for experience a software failure, a software fault statement should be executed and should be located on the execution path. As you know, when we execute a program, and execution, all execution passes not experienced, but one of them experienced. It may be that the faulty statement is not located on that execution path, so the software failure is not experienced. Okay. In software testing, we try to design inputs or to detect inputs that will show more faults, more failures in the software. Okay. The art of the engineer is that finding good test cases, good input data, good input data, the inputs that cover all execution passes, maybe making a good test set. So we try to find out, to look for inputs that will show the faults, that will execute the faults. Therefore, we sampling the inputs that cover many execution passes of the program as well as possible. What I explained in the previous lecture, there is a question that when a fault trigger a software failure, or when a fault leads to a software failure. Informally, I explained this problem, this question in the previous lecture, but in this slide and later, we are explaining this problem formally and we explain it more deeply. Note that there are 4 conditions necessary for a failure to be observed by the user or by the tester. These 4 conditions is 1. Reachability, infection, propagation, and reveal. What is the reachability? What's the meaning of reachability? Then reachability is that the faulty statement of the software could be reached from initial state of the program, or the faulty state be executed in the execution path, in our execution path, by our testers. In this, the reachability is defined as the location or locations in the program that contain the fault must be reached. Must be reached. Not all, you should note that not all statements of the program reachable. For example, get codes, statements of the return statement of the method could not be reached and located on any execution path. So the reachability and the execution of the software of the faulty statement is essential. Is the first condition to trigger a software failure. The second one, as I said, is infection. What's the meaning of infection? The infection is that the state of the program must be incorrect. We have defined the program state in previous lecture. The program state is defined by the values of internal variables of the program. When the value of some internal variable changed by any statement of the program, the state of the program changed also. So, if the state of program is incorrect, we have an error state. And we could say that the state of the program is infected by some faulty statement, by execution some faulty statement. Actually, when we execute a faulty statement, we change the software, the state of program to an incorrect state probably. An incorrect state. Because the execution of a faulty statement may lead to an incorrect setting in internal variables of the program. So the infection is the second condition that is necessary for a trigger failure in software products. The next one is propagation. What's the propagation? When the infected state, when an error state causes some incorrect output at the final state of the program, we say that the incorrect portion of the error state propagated across the execution phase. We explain this more in the next slide by a state transition model. So we postpone more explanation for this term to the next slide. The last one is reveal. What's the meaning of reveal in this context? To observe failure, to see software failure, the tester or the user must observe part of the incorrect portion of the program state or final program state. The output of the program is extracted from final state of the program. When we pass an execution pass, in the after execution, just after the last statement of the program, the final program state is made, and the output is made from some internal variables of the program at the final state. So if the portion is some variable in that portion of the final state that should be shown to the user or observed by the user is incorrect, we say that the software failure could be observed. Software failure is happening. Okay. I think that there is some ambiguity in software state or program state in your mind, so note that this slide is a bit different from those in the course homepage. Some of the slides I changed them for more illustration, for more illustrative. So by this example, we try to explain more about these four conditions of for triggering software failure. In this Java code, in this method, we try to find an element in an array, and we report the last occurrences of the element in the array. The array maybe consists of element more than one. So we try to find the location of the last occurrences of the n element in the array. To do this, in the first statement, a variable last index is defined and initialized to -1. By default, we consider that n is not located in any of the array elements, and array did not consist of n by default. So we should check the elements one by one and compare with the n. If we find the element n, we should change the last index in this method. For this, we use a for loop with variable I as a counter and initialize by 1 incorrectly. Also in this code, this is an incorrect statement. Because in Java and C++, as I said before, the array started with 0 index. Okay. So in this for loop, while there is an element in the array, we should compare the element with n by n in if statement. And if we find the n element, the last index changed to the current value of f. This is done for all elements of the array except the first one. And at the end, the last index is returned by the method as an output experiment. So we want to explain you how the states of program is defined by executing this method, and how the states of the program changed by executing each statement of the program. To do this, to explain this important subject, we use a state transition system. This diagram is an state transition system. Once the method is called by any input, the first state is formed by these two variables, a and array a and an integer. For example, for calling the method for this array that consists of 2, 3, and 5 elements, and an integer n which equals to 5, this state is formed by the OS for this program. This is the state of the program. For some simplicity, we ignore the CPU registers such as program counter, instruction register, data register, and so on. We just showed the internal variables of the method in this state transition diagram. So, this is the first state. This is the start state, primary state, which consists just input variables. By the execution of the first statement of this method, the statement of our program is changed to the next one. In the next state, we have new variable named last index and set to -1. This state is different from the previous because in this state we have 3 variables. In the previous we have just 2 variables, a and n. So this is done by the execution of this first statement. As we go ahead, we read the for loop and the initialization of its counter I as the first statement of the for loop. By execution this initialization, the state of the program also changed. And we go to the next state. In the next state, we have one new variable other than the previous. The variable I is added to the new statement, and we have a statement that's different from the previous. In this statement, we have 4 variables. As you know, this is an error statement, because in this statement we should have value 0 for counter I instead of 1. So this is an incorrect state, and we say that firstly, the incorrect statement is reachable from the first state of the program. The incorrect statement, the faulty statement, is reached from the first statement, the first state of the program, which means reachability. This faulty statement is reachable from the first method. So it is reachable. The reachable is provided in this example. And as you see, this state is a faulty state, is an incorrect state, is an error state. So the infection condition is provided too. The reachability and the infection is provided by this example. But as we continue the execution of this for loop, in the next execution, in the current execution, the element located in index 1 means 3 is compared with n, which is 5, and this two is not the same. So the last index doesn't change in this execution, the current execution. And for the next execution, the I is incremented as stated in this statement. I is incremented to 2. And in the next execution, this time, we just change from this statement to the next statement, in which the I value of I changed from 1 to 2. In this statement, as we execute the body of the for loop, and as you know, the value of last index should be changed, because the elements that we look for it is located in this location. So in this statement, when we execute this if statement, and the last index changed to 2, not that last index is changed to 2. Okay? As you know, this state and this one is correct. There is no problem in this statement. All variables are set to correct values. And we say that the final state is true. So we summarize that the infected state, the incorrect variable, does not propagate through the execution path. This is an execution path. This incorrectness does not affect later states of the program. the final statement, the final state of the program is true, because the 5 that we look for it is located in index 2 of this array, and the last index is correctly set to 2. So this final state is correct and not affected by the execution of this faulty statement. So in this case, my test input do not trigger a software failure, because the error state is not propagated to the final state. But in the next one, please note that this is a test case that triggers the software failure. In this test case, this is a test data input value. In this test data, the array is the same as the previous, but with different order. In this version, in this test data, the 5 value, the 5 element, is located in the first position of it. And obviously you know that this is not checked by this method. The first position is not checked by this method. So the result of this method should be incorrect for n5, n equals. Okay. As you know, this faulty statement is reachable, as you've seen in the previous slide, and it affects this statement, and this incorrectly statement affects the later statement, because in the next statement the last index should be changed to 0, but this is not done by this execution. So we say that this incorrect state, this error state, affects the next state, and this affects the next one until the final state. We say that the final state is incorrect because the last index is not set correctly. Okay, and in this method, as you know, the last index, which is incorrect, which has incorrect value, is also the output variable, and it is seen by the user or tester. So this test data reveals some incorrect computations in this method for the user, because the value of this variable could be seen by the user. It's actually the output of the method, and computes and saves the actual result. in this execution for these inputs, we expected the output be 0. But in this execution, we saw the actual output as -1, which is different with 0. So we say that a software failure happened. And this is visible for the tester and the user. So this reveals the software failure. So we summarize the 4 conditions for triggering a software failure: reachability, infection, propagation, and reveal. And this is showed in this model named as RIPR model, which is the abbreviated of reachability. R stands for reachability, I stands for infection, P for propagation, and R for revealability. In software testing, we should try to define test cases, to design test cases in which the execution of it reaches the fault statements. So the reachability should be provided to reveal software failure, and faults should be propagated, should be infected, faults should infect the program state and leads to an incorrect program state, leads to an error state. So the fault infects the program state, and when the program state propagated to the final state, we have an incorrect final state. As you see, the program final state may be bigger than the incorrect portion. But when we return the actual result, we just show some variables in this final program state. As the observed state of the final state is defined in this case by this area. As you see, this area has not an intersection with this area, and these two areas are not overlapped. There is no overlapping for these two areas. So the user, the end user, the tester, does not see the incorrect portion of the final program state, and it could not be the test could not be revealed the software failure, could not reveal the software failure. But when the observed program state changed to this area, and this observed portion overlapped partially with the incorrect portion of the final state, we say that the user and tester saw the outputs incorrectly. So the incorrect output, and this will reveal the software failure. For diagnosing this failure, we use a test author. The test author defines the expected result for variables that users need to meet. The expected result is defined by test author and compared with the actual result. The actual results is defined by this area of the final program state. If this is not the same as values defined by the test author, we say that the software failure happened. And for this, as you know, this small portion of the expected result, of the actual result, is incorrect. So, the actual results differ from expected results determined by test author. This is our IPR model. Excuse me. In this slide, some of the software testing activities are introduced for you. The first one is test engineer. Who is the test engineer? The test engineer is an IT professional who is in charge of one or more technical activities. What are the technical activities? They consists of designing test inputs, input data, sampling the input data from a wide input space of the program as our test cases or as our test inputs, producing test values, running the test scripts. Another activity is analyzing the results of testing, which tests are passed, which are failed, and finally reporting the results to the developer team and testing manager and development managers. These are all of technical test activities, and the test engineer is responsible for doing some of these activities. But the test manager is whom that is in charge of one or more test engineers and do some works such as setting test policies and defining the processes of software testing and approaches of software testing, and interact with other managers of the development team of the project, and support all test engineers. So in this slide we learn some software testing activities and who is responsible for any of these activities. We introduce just two types of testing engineers, which is test engineer and test manager. In this section 2.1 in your textbook, the traditional testing levels are introduced. As you see in this image, our program has three classes. Class P, the class P contains of the main method of the program, which execution of the program is started from the main method of class P, and two other classes, class A and class B. As you see, class A has two methods, and this is true for class B. Class B has again two methods, and this method could call each other according this relationship, according this edge. This edge show the communication of this method, the connections between these methods. For example, this edge shows that the method M1, for example, can call the method MB1 of class B, or vice versa. And also at the same time, the connection between methods of two different classes define the interaction of two classes. This is an inter-method relationship. Inter-method relationship. Or this is inter-method. This defines inter-class relationship. Inter-class relationship. This is inter-method of one class, but this relationship, this communication defines inter-class or interoperability. As you have experience in your programming exercises, when we test each method individually, we have done unit testing. In this context, the unit is a method. When we test, we observe the executions of a method individually. We just doing unit testing. And you know that unit testing is done by developer, by programmer. Each programmer done his unit testing by himself. This is unit testing. As this arcs show, in this program we should do 4 unit testing, because we have 4 methods in this program. Also, the main method located in P should be tested later. This is not the first step. This method is tested after all, and the next level of software testing. In the first level, the unit testing is done, and because these units are tested individually, the units of these classes is 4. is done in unit testing level. The next level of testing is module testing, which is also done by programmer, by developer. In this level, we test each class. Each class is tested individually, or each component, each file is tested individually. And this type of testing is done also by developer. As you see by these arrows, we should do 3 module testing. We have 3 module testing. Because we have 3 classes in this program. In the next level, we have two doing interaction testing. In interaction testing, we observe the communication, the interaction between components, between modules. As you see, in interaction testing level, we test these connectors, these communications. As you see, in interaction testing, we test inter-class relationships, inter-class communications, and we observe the behavior of communication between modules. The next level of testing is system testing, which tests the overall functionality of the system. When we doing system testing, we test actually the main method of the class P, because the main method of class P defines the overall functionality of the system. If the main method passes its test cases, we say that the system testing is done. So the system testing is the final level, is the last level of testing that should be done by developer team, by testing team. But there is another level which should be done by users, which is the acceptance testing. The acceptance testing, the software is the product is tested whether it is acceptable for the end users. This level usually is done by end users. Okay, so we have in traditional view, in traditional testing levels, we have 5 levels which started from unit testing, extending by module testing, then we're doing integration testing, and finally we're doing system testing. And for deployment, for delivering to the end users, we should testing the acceptance of product. In this stage and this level, We should test the product against the requirements that's defined in a requirement document or in the analysis documents. Okay. But in another view, which stated against the traditional view, means object-oriented testing view. We have some different, actually 4 different levels of testing. In this testing categorization, we have to test method individually. So we should test intra-method inside of a method. We should test the functionality of each method individually, and we should test method insides of the method. This level is named intra-method testing. In this example, we should doing 4 intra-method testing, which test each method individually. In the next level of object-oriented testing, we should test inter-method testing. As you see, there is a single inter-method of testing. In this level of testing, we just test interactions between methods of the same class. Test pairs of methods in the same class. So, the first level, intra-method testing. The second level, inter-method testing. And the next one is intra-class testing. In this level, we test an entire class as a component, as a module, or as sequences of calls. This is intra-class testing. And the last level in this view is intra-class testing, which tests the communication, the interoperability between 2 classes. Test multiple classes together. Test interactions between classes. So in this view of object-oriented view, we have 4 levels of testing. It includes intra-method testing, inter-method testing, intra-class testing, and inter-class testing. This next slide defines coverage criteria for this. This is enough for this lecture. Try to study your textbook and assess your learnings in this context. If you had a problem, if you have ambiguities about this concept, you could ask me your questions in next session of the class, and I hope I can answer them properly. See you. Class P, because the main method of class P defines the overall functionality of the system. If the main method passes its test cases, we say that the system testing is done. So the system testing is the final level, is the last level of testing that should be done by developer team, by testing team. But there is another level which should be done by users, which is the acceptance testing. The acceptance testing, the software is the product, is tested whether it is acceptable for the end users. This level usually is done by end users. Okay, so we have in traditional view, in traditional testing levels, we have 5 levels which started from unit testing, extending by module testing, then we're doing integration testing, and finally we're doing system testing. And for deployment, for delivery to the end users, we should testing the acceptance of product. In this stage and this level, we should test the product against the requirements that's defined in a requirement document or in the analysis documents. Okay. But in another view, which stated against the traditional view, means object-oriented testing view, we have some different, actually 4 different levels of testing. In this testing categorization, we have to test method individually. So we should test intra-method inside of a method. We should test the functionality of each method individually, and we should test method insides of the method. This level is named intra-method testing. In this example, we should doing 4 intra-method testing, which test each method individually. In the next level of object-oriented testing, we should test inter-method testing. As you see, there is a single inter-method of testing. In this level of testing, we just test interactions between methods of the same class. Test pairs of methods in the same class. So, the first level, intra-method testing. The second level, inter-method testing. And the next one is intra-class testing. In this level, we test an entire class as a component, as a module, or as sequences of calls. This is intra-class testing. And the last level in this view is intra-class testing, which tests the communication, the interoperability between 2 classes. Test multiple classes together. Test interaction between interactions. Four levels of testing includes intra-method testing, inter-method testing, intra-class testing, and inter-class testing. This next slide defines coverage criteria for this. This is enough for this lecture. Try to study your textbook and assess your learnings in this context. If you had a problem, if you have ambiguities about this concept, you could ask me your questions in next session of the class, and I hope I can answer them properly. See you next session. Goodbye. Properly. See you next session. Goodbye. See you next session. Goodbye.